Hey there, Calc kids. Today we're going to look at 3.4 velocity and other rates of change. It's everything we've been doing. We're just going to put other names to it. So let's get to it. Instantaneous rate of change. What that says is instantaneously at a given moment we can find the rate at which it's changing. That's your first derivative. This is what I write down. The instantaneous rate of change of a function with respect to x at a at some point is its derivative. And then it gives you the old formula, right? We don't need that anymore because we're studs. We know this. We know how to do it shortcut way now. So that rate of change is an instantaneous moment in time. Okay. So let's do an example where we use the terminology instantaneous rate of change. So the area of a square as a function of its radius is area equals pi r squared. Area a circle. That's silly. Okay, so we need to find the rate of change to the area with respect to the radius r. Okay, to do that we need to find a prime. The derivative. A prime will give us the instantaneous rate of change formula. So we take our 2 and we move out in front. 2 pi, because remember pi is just a constant, guys. This original formula is pi times r squared. So we get 2 pi r. 2 moves out in front. 2 minus 1 is 1. Now, I want you to think about something. Oh no, I got to adjust it. The area of a circle is pi r squared. Its derivative is 2 pi r, which is the circumference. If you don't find that interesting, I don't know who you are. That you can take. So that means your circumference gives you the rate of change of a circle at the given moment its radius is changing. Okay. I'm going to show you some other cool stuff you can do with derivatives and integration. How to derive your own formulas. Derive your own formulas. Do you see where that came from? Derive. Okay. So now let's do it when r equals 4. Always plug it into our a prime formula. 2 pi times 4 is 8 pi's. And that is our rate of change at the given moment of 4. When your radius is 4, your area is changing at a rate of 8 pi per whatever your time is in which you are using. Okay. The displacement of an object over the time interval is from t to t plus delta t is delta s is f of t plus delta t minus f of t. This is a fancy term of how far are you from the start. If you started at 3 and you end up at 2, you went -1. That's your displacement. If you start at 3 and you go to 100, your displacement's 97. See how I did that pretty quick, huh? So it's how far you moved. Your average displacement, okay, is displacement over time traveled, which is your derivative. So we're going to call it, let's go d over dx. Okay. And you might be asking me, when am I going to use this? I'm going to show you guys some examples with this with particle motion. Well, I'm not going to show you the particles moving, but I'm going to show you an example of which they said the particles are moving. Okay. 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 Instantaneous velocity is the same thing as the instantaneous rate of change. Okay, so really all I want you to know is the instantaneous velocity is the derivative of its position function. Okay, so there's going to be a function that tells you where you are at a given point, and the derivative tells you your speed at that point. I don't So we have a position function. Our derivative gives us the average velocity function. First derivative average velocity. If your original gives you your position. Okay. Just a little quick tidbit, something to keep in mind. Velocity can be negative, right? If I start moving backwards, that's a negative velocity because I'm moving away from you. But if I'm moving closer, that's a positive velocity. Speed is always positive. Okay? Speed includes distance, or doesn't include distance. So with speed, I'm going backwards and forward. I'm going the same speed all the time. Okay? But I'm going positive velocity, negative velocity, positive velocity, negative velocities. Same speed. Speed's always positive. Are we good? Now, bias velocity is your first derivative. Acceleration is going to be your second derivative. I kind of already told you this. And the third one's going to be a jerk. We'll know that's what it's called. It's jerk. G-E-R-C. Capital J-E-R-C, actually. If someone can look up, here's a John answer quest, maybe in Smarties. If you can find to me the origin of where jerk comes from for this third derivative, okay? First one to get to me, you win. Congratulations. Second derivative, acceleration though. Here's some stuff that's going to come up. They're your free fall constants on Earth, because that's where we live. This is all important. Okay. English units is going to be 32 feet per second squared, because that is the acceleration due to gravity. Okay. Your speed is going to be equal to your 16t squared, or your position one. So you can see it's just a derivative. Are you done writing it? Go. Suppose you take a projectile and shoot upward from the surface of the Earth and it reaches a height of s equals negative 4.9 t squared plus 120 t meters at t seconds, find velocity after 5 seconds. Okay, this gives us position. This original formula gives us position. So in order to find velocity, we need to find s prime. Will give us our velocity. Okay, so s prime is going to be negative 9.8. And I got that 9.8 because 2 times 4.9 is 9.8. T plus 120, because derivative of 120t is 120. Okay. So we're looking at after 5 seconds. So we plug in our 5 for t. And we plug that in, we get 71 feet per second. Okay, and it's a positive velocity because they're going in a positive direction. So take first derivative, plug in your number, it gives your instantaneous velocity. Some people say that the first derivative is a measure of sensitivity of the rate of change at which a function is changing. I don't usually call it sensitivity. Maybe I need sensitivity training. I'm sorry. I don't really see that as very important. This is okay. Economists came up with a special vocab for rates of change and derivatives. They could have just said the rate change, but they decided to go and make their own because they're economists. And if you know any economists, you know they're kind of odd ducks. I'm one to talk, I know. Anyway, they call them marginals. Okay. What it is their derivative, the marginal cost production, is the rate of change as opposed to production. So pretty much your first derivative of production gives you the marginal cost of production. Take profit, take the first derivative, that's your marginal profit. Okay, no, that's it, that's all I got. So that's kind of like, if we make one more unit, what will that cost us at that given point? So if you take business calc, you'll see where it's used more. But let's do one example. You're gonna make washing machines, right? I'm gonna make a machine that washes washing machines, so I'm gonna be a millionaire. You're a hundredaire. Okay, this is our cost, right? So we want to find the marginal cost of producing 100 washing machines. Well, our marginal cost is going to be C prime of x, right? Moby, what are you doing? It's dying. Which is going to be, the 2,000 goes away. It's going to be 100 minus 0.2x. Because 2 times 0.1 is 0.2. Okay? So now what we do is we plug in the 100 to find our marginal cost at 100 washing machines. And we plug that in, we get $80, we'll say, is our marginal cost. I'd write more, but my Moby's died. Enjoy. Have a good day.